Raise your hand in front of a mirror, and the figure in the glass raises the opposite one. Step closer, and it comes to meet you. Exactly, and reversed. Hold that image, because one of the world's leading cosmologists believes it is the truest picture we have of the beginning of the universe. Not an explosion, not a wall of fire, a mirror. Neil Turok, who worked beside Stephen Hawking, says Einstein's equations pass straight through the Big Bang, and that on the other side stands a reflection of everything. Our universe, reversed in space, reversed in time, made of antimatter. No new particles, no extra dimensions, no inflation, just the laws we already have, and 5 numbers that describe the entire cosmos. By the end of tonight, you will know the simple theory that explains everything, and the single measurement, already underway, that will prove it or kill it. Before we begin, if you like ending the day with the universe quietly rearranged, a quick like or subscribe truly helps, and it keeps me making these. It is a small kindness. Now, let's ease in. There is a habit at the heart of modern physics, and it is so old and so successful that almost nobody thinks of it as a habit anymore. The habit is this: when the universe presents you with something you cannot explain, you add something new. A new particle, a new field, a new force, a new dimension. For most of the 20th century, this habit was not just a strategy. It was the engine of the greatest intellectual winning streak in human history. Consider how well it worked. At the start of the 20th century, physicists knew about electrons and protons, and not much else. Then the structure of the atomic nucleus refused to make sense, and so theorists proposed that protons and neutrons were not fundamental at all, that inside each one lived smaller particles called quarks. It sounded like an accounting trick. It turned out to be true. The quarks needed something to hold them together, and so physicists added gluons, the carriers of the strong nuclear force. Those turned out to be real too. New accelerators came online, smashing particles together at higher and higher energies, and out of the debris came particles nobody had asked for, heavier cousins of the electron, heavier cousins of the quarks, whole extra generations of matter, as if nature had printed its parts list in triplicate. Each surprise was absorbed the same way. Add it to the list, extend the table, build a bigger machine, and find the next one. By the late 1970s, this process had produced one of the most successful structures in the history of thought, the Standard Model of particle physics. It describes the electron and its 2 heavier siblings, the 6 quarks, the 3 neutrinos, the photon that carries electromagnetism, the gluons that carry the strong force, the W and Z particles that carry the weak force, and the Higgs particle that gives the others their mass. It is written in the language of quantum field theory, and it is constrained, brutally constrained, by the twin requirements of quantum mechanics and relativity. Those requirements are so severe that the whole edifice runs on only about 20 adjustable numbers. 20 numbers sounds like a lot until you hear what those numbers buy you. They buy you correct predictions for millions, arguably billions, of separate measurements. The magnetic behavior of a single electron has been calculated within this framework and checked against experiment to roughly 1 part in a billion. That is like predicting the distance from New York to Los Angeles to within the width of a human hair using nothing but mathematics written on paper. So, the habit worked. That is the point, and it is also the problem, because here is the strange thing that happened next, the thing that this entire evening turns on. Around 1980, the adding stopped working, not gradually, almost all at once. The theoretical ideas of the Standard Model were essentially complete by the end of the 1970s, and then physicists did what they had always done. They built bigger machines, and they waited for the next layer of surprises. The machines came. The surprises did not. Accelerator after accelerator turned on, ran for years, and found precisely what the Standard Model said they would find, and nothing else. The largest of them all, the Large Hadron Collider, outside Geneva, a ring of superconducting magnets 17 miles around, colliding protons at energies that recreate conditions from a trillionth of a second after the Big Bang was built, with the confident expectation that it would uncover a whole zoo of new particles. It found exactly one new particle, the Higgs boson. And the Higgs was not a surprise. It had been predicted in the 1960s. Finding it was a triumph of engineering and a confirmation of old theory. It was not a discovery of anything new about the world. It was the last item on a 50-year-old shopping list, finally checked off. Meanwhile, the theorists had kept adding anyway, on paper. This is where the story takes a turn that will matter for everything that follows tonight. In the early 1980s, the fashionable idea was grand unification, the proposal that the strong force, the weak force, and electromagnetism were all fragments of a single, more symmetric superforce. The Standard Model has, in a certain sense, 12 force-carrying particles, 8 gluons, 3 weak bosons, and 1 photon. The simplest grand unified theory promoted that to 24. The hope was that adding more would make everything simpler, the way a finished puzzle is simpler than a pile of pieces. It did not work out that way. To break the big, beautiful symmetry back down to the messy world we actually observe, theorists had to add still more fields, more parameters, more arbitrary choices. The unification giveth, and the fine print taketh away. One of that theory's cleanest predictions, that protons should occasionally decay, has been tested by watching enormous tanks of water underground for decades. The protons have declined to decay. Then came supersymmetry, which proposed that every known particle has a hidden partner, doubling the entire contents of the universe in one stroke. It was elegant. It was beloved. Its simplest version is now ruled out by experiment. Then came string theory, which replaced point particles with tiny vibrating strings and required for its own consistency 6 extra dimensions of space curled up too small to see, and which came with not just a few new particles, but an infinite tower of them. And, when string theory turned out to come in too many varieties, it was gathered up into something called M theory, which needed yet another dimension. Each step was mathematically rich. Each step was pursued by some of the most brilliant people alive. And each step moved physics further from anything an experiment could check. Somewhere along the way, a field that had spent a century being disciplined by measurement drifted into a place where the measurements could no longer reach. Now, you might expect the physicists themselves to be the last people to say this out loud, and mostly you would be right, which is why tonight's story is unusual, because one of the most decorated theoretical cosmologists alive, a man who held the chair of mathematical physics at Cambridge, who directed one of the world's leading institutes for theoretical physics for more than a decade, who worked beside Stephen Hawking on the deepest question there is, and whose own doctoral advisor helped invent superstring theory, has spent recent years making an argument that sounds, at first, almost like heresy. His name is Neil Turok, and his argument, stripped to one sentence, is this: the era of adding is over, because there may be nothing left to add. Turok puts it with a calm that makes it more unsettling, not less. Perhaps, he says, we already know all the laws of physics. They are sitting in front of us. Einstein's theory of gravity, the Standard Model of particles. Every accelerator built in the last 40 years has, in effect, been asked the question, is there more? And every one of them has answered, not that we can find. Most of his colleagues treat that silence as a temporary embarrassment, a gap between machines. Turok treats it as data. What if the silence is the answer? What if the inventory of nature is complete? And the real task, the task physics has been avoiding for half a century, by inventing ever grander things to look for, is to understand how the pieces we already possess fit together. That question sounds modest. It is not. Because there is one place where the known laws of physics have always, publicly, catastrophically failed. One place where everyone agrees that something is missing. That place is the beginning. The Big Bang, the moment where Einstein's equations drive the whole universe down to a single point and then give up. For 50 years, the assumed lesson of that failure has been, we need new physics. New fields, new eras, new machinery, bolted onto the first instant of time. Nearly every cosmologist alive has built their career on some version of that assumption. Turok is proposing something else. He is proposing that the beginning of the universe was never broken at all, that the laws we already have handle it perfectly and have been handling it all along, if only we read them correctly. And the way to read them correctly, he says, involves one of the strangest, simplest ideas ever offered about the origin of everything. The idea that the Big Bang is not a wall, and not a birth, and not an explosion. The idea that the Big Bang is a mirror. What that means, what it could possibly mean for the beginning of time, to be a mirror, is where we are headed tonight, one careful step at a time. But before we can stand in front of that mirror, we need to see what Turok saw first. We need to look at the universe the way a minimalist looks at it. Because it turns out that when you tally up everything, the cosmos actually requires not what our theories would like it to require, but what the sky itself demands. The answer is so small, it fits on the back of your hand. Here is a question that sounds like it should have an impossibly long answer. How many numbers do you need to describe the entire universe? Think about what the question is really asking. The universe contains something like 2 trillion galaxies. Each galaxy holds, on average, 100 billion stars or more. Around those stars orbit worlds beyond counting, and between them drift clouds of gas and dust, light years across. And threading through all of it runs an invisible scaffolding of dark matter, and underneath everything, space itself is stretching. Describe all of that. Every cluster, every void, every filament of the cosmic web. How many numbers would you need? The answer, it turns out, is 5. Not 5 million, not 5,000, 5. This is one of the most remarkable discoveries of the last 100 years, and it is strangely under-celebrated. If you take the standard model of particle physics, the 20 or so numbers we met a few minutes ago, and you ask what else must be specified to describe the universe on its largest scales, everything cosmologists have ever measured comes down to 5 additional quantities. Turok himself lays them out, like a man setting 5 stones on a table, and it is worth holding each one for a moment, because by the end of tonight, this list will come back with a very different meaning. The first number is the cosmological constant, often called dark energy. It tells you how much energy is contained in empty space itself, in a perfect vacuum, with everything removed. That energy pushes the universe's expansion to accelerate, and its measured value is tiny but stubbornly not zero. The second number is the amount of dark matter compared to ordinary matter. For every kilogram of the stuff you and the stars are made of, there are roughly 5 kilograms of something invisible whose gravity sculpts the galaxies. The third number is the ratio of baryons to photons, how many protons and neutrons exist for every particle of light. That ratio was fixed in the universe's first moments, and it comes out to roughly 1 particle of matter for every billion or so photons. 3 numbers for the contents of the universe: the energy of nothing, the weight of the unseen, and the ratio of matter to light. The last 2 numbers describe not what the universe contains, but how it began to take shape. The early universe was almost perfectly uniform, almost. Spread through it were tiny variations in density, places very slightly denser than average, and places very slightly emptier. Those variations were the seeds of everything. Over billions of years, gravity pulled matter toward the denser spots, and the denser spots became galaxies, and the galaxies became clusters, and the slightly emptier places became the great voids. We can still read those primordial variations directly because they are printed on the oldest light in existence, the cosmic microwave background, the afterglow of the hot early universe, arriving at our telescopes today from a time before any star existed. The fourth number is simply the strength of those variations. It is about 1 part in 10,000. The infant universe was smoothed to 1/100th of 1%, and that whisper of unevenness was enough to build everything you have ever seen. Pause on that fourth number for a moment, because its smallness is easy to say and hard to feel. 1 part in 10,000 is the unevenness of a pond whose surface, across a mile of water, never rises or falls by more than the thickness of a leaf. If the early universe had been perfectly smooth, 0, instead of almost 0, gravity would have had nothing to grip, and the cosmos today would be a thin, cooling, featureless gas. No galaxies, no stars, no planets, no one to notice. If the ripples had been much stronger, matter would have crashed together too eagerly, collapsing into black holes before stars could form and shine. The universe we know lives inside. That whisper, everything you have ever loved, grew from a wrinkle 1/100% in depth. The fifth number is the subtlest, and it will matter enormously later tonight, so let it settle in gently. When scientists analyzed those primordial ripples, they found the variations come in all sizes: small ripples, medium ripples, ripples spanning enormous stretches of sky, and the strength of the ripples is almost exactly the same at every size. The pattern is what physicists call scale invariant. Zoom in or zoom out, and it looks statistically identical. Almost. The longer ripples are very slightly stronger than the shorter ones, stronger by about 4% for each doubling in size. That small tilt has been measured with exquisite precision, 4%. Remember that number. It is a fingerprint, and before tonight is over, you will hear whose fingerprint it may be. And there is one more property of those ripples, perhaps the most haunting of all. Their statistical character is the simplest that mathematics allows. They are what is called Gaussian random noise, the same bell curve randomness you get from adding up many small independent accidents. No intricate patterns, no hidden code, no favored directions. The universe's opening statement, read off the sky by satellite after satellite, is the plainest possible static, tilted by 4% at a strength of 1 part in 10,000. So let us take stock of what the sky itself is telling us, because it forms the spine of everything that follows. The universe, on the largest scales anyone has ever observed, is described by the standard model of particle physics plus 5 numbers. 25 numbers or so, all told, for everything. And the initial conditions were not baroque or elaborate. They were the simplest imaginable noise. Nature, at both its smallest scales and its largest, appears to be almost pathologically economical. Now hold that up against the theories we met in the last chapter. Grand unification wanted dozens of new fields. Supersymmetry wanted to double every particle in existence. String theory offered 10 dimensions and an infinity of vibrating states, and its landscape of possible universes runs to numbers like 10 to the 501, followed by 500 zeros. The most influential theory of the universe's first instant, cosmic inflation, comes in tens of thousands of published variants. There is a mismatch here, and it is not subtle. The universe we measure is lean. The theories we built to explain it are extravagant. It is as if someone described a plain white room using the complete works of an ornate architecture catalogue. A skeptic could fairly reply, so what? Nature does not owe us economy. Perhaps the extravagant machinery is all there, hiding at energies we cannot reach, and the leanness is an illusion of distance. For decades, that has been the standard reply, and it is not foolish. But notice what kind of reply it is. It asks us to believe in an enormous hidden inventory for which the evidence is, so far, absence. Every accelerator, nothing new. Every dark matter detector, tons of liquid xenon buried beneath mountains and watched for years, nothing yet. Every survey of the primordial sky, the same 5 numbers, sharpened to more decimal places. At some point, a scientist is permitted to take the universe at its word. That is precisely what Turok decided to do. His philosophy, in his own phrase, became one of extreme minimalism. Explain everything we see with the minimum number of theoretical ingredients. And he is quick to point out that this is not some eccentric personal aesthetic, it is the oldest rule in science, Occam's razor. When a simple explanation and a complicated one both fit the facts, take the simple one, because the simple one is the one that can be tested and the one that predicts. Maxwell's theory of electromagnetism has no adjustable parameters at all, and it governs every radio wave, every beam of light, every flicker of electricity on Earth. Einstein's theory of gravity is nearly as rigid, and it has passed every test from falling apples to colliding black holes. Those theories are interesting precisely because they are not adjustable. They stick their necks out. The extravagant frameworks of the last 50 years, Turok argues, never really did. But if you take minimalism seriously, if you truly commit to explaining the world with only the ingredients in hand, then you inherit a terrifying obligation. You do not get to hide anymore. Every one of those 5 numbers becomes a debt you must pay with known physics. The energy of empty space. Explain it. The dark matter. Identify it, using no new particles, or at least none beyond what the standard model already quietly requires. The 1 part in 10,000 ripples and their 4% tilt derive them. From what? From the same equations that run your microwave oven? It sounds impossible. Hold the thought, because the claim coming later tonight is precisely that this has now, tentatively, been done. And looming behind all 5 numbers stands the debt nobody has ever paid, the place where every theory, minimal or extravagant, has always come to grief. The numbers describe how the universe evolved. They say nothing about how it began. Follow the expansion backward, run the film in reverse, and you arrive at the moment where the whole 2 trillion galaxy cosmos converges to a single point, and the equations themselves catch fire. The singularity, the beginning, the oldest unpaid debt in physics. If extreme minimalism is going to survive, it has to walk into that fire with nothing but the laws we already have. So that is where we go next, backward, all the way down, to the sharp tip at the bottom of time. Every story about the mirror has to begin with the thing the mirror replaced. And the thing the mirror replaced is, by common agreement, the most fundamental mystery in all of physics. The singularity at the beginning of time. The evidence that our universe is expanding is now almost a century old. Distant galaxies are receding from us, and the farther away they are, the faster they recede, not because they are flying through space like shrapnel, but because the space between us and them is stretching. That discovery, made in the 1920s, carried an unavoidable implication that took decades to sink in. If everything is moving apart today, then yesterday everything was closer together. Last year, closer still. And if you keep running the film backward, 1,000,000 years, 1,000,000,000 years, 13.8 billion years, you arrive at a moment when everything was on top of everything else. Not matter, crowded into a small region of space. Space itself, all of it, shrunk toward no size at all. This is what Einstein's equations imply, and it is worth being clear about how seriously physicists take those equations. General relativity is not a sketch or a metaphor. It is a precise mathematical machine that has predicted the bending of starlight, the slowing of clocks in gravity, the existence of black holes, and the exact chirp of gravitational waves from black holes colliding over 1 billion light-years away. When that machine speaks, physicists listen, and when you feed it a universe like ours and run it backward, the machine says singularity. A point of infinite density and infinite temperature, where the distance between any 2 things goes to 0, and the equations return infinity after infinity, which is a polite way of saying they stop returning anything at all. For a while, physicists nursed a hope that the singularity might be a kind of mathematical accident. Maybe it only appears if you run the film backward too perfectly. The real universe is lumpy and imperfect, maybe, in a realistic universe. The collapse would miss itself, everything swinging past everything else, like a crowd that never quite collides, and the singularity would dissolve into an innocent, dense phase. That hope was killed in the 1960s, and one of the people who killed it was Stephen Hawking. What Hawking and his colleagues proved with mathematical certainty, not simulation or estimate, is that in general relativity, a universe like ours cannot avoid the singularity. No amount of lumpiness saves you. If Einstein's equations hold in real time, all the way down, then time itself has an edge. There was a first moment, and the equations cannot speak about it, and they cannot speak about anything before it, because in the mathematics, there is no before. Let me try to give you a feeling for what this actually means, because it is stranger and more intimate than the textbook language suggests. Picture the whole history of the universe as a shape Hawking's own picture, the one Turok inherited. Imagine a cone standing on its tip. Time runs upward along the cone. Space is the cross-section. Slice the cone horizontally at any height, and the circle you get is the universe at that moment. Up here, near the top, the circle is wide, that is today, 2 trillion galaxies with room to breathe. Slide your hand down the cone, and the circles shrink. The galaxies crowd together, then dissolve into hot gas, then into plasma, then into a sea of naked particles, hotter than the core of any star, and now you are falling with it. The whole observable universe, everything you have ever seen, every star, in every catalogue, closes around you, contracting through the size of a galaxy, of a solar system, of the room you are lying in now. The light around you sharpens from orange heat to white to colours no eye could survive. The universe passes through the size of a coin. Nothing has broken yet. The equations are still speaking calmly, the way instruments read normally right up to the second a plane hits the ground. The size of a dust grain, the size of an atom, smaller than the width of a proton, and still shrinking, and the temperature is now beyond every number with a name. And you look down and see it coming up at you, the tip, the place where the cone simply ends, the last point. You brace for the moment of arrival, the moment the film begins, and there is no moment. The mathematics does not show a beginning happening, it shows the page torn off. Above the tip, a universe. At the tip, infinity. Below the tip, not emptiness, not darkness, not silence, no below. That tearing off is what physicists mean by the singularity, and it should bother you. It bothered them, because a theory that predicts its own breakdown at the very first moment is a theory confessing that it cannot explain why anything exists. Every event in your life had a cause that preceded it. Every star formed from a cloud. Every cloud from an earlier cloud. Science runs on the confidence that you can always ask, and what came before that? At the tip of the cone, the question is not answered. It is disallowed. And if you try to escape the tip by imagining that time simply extends forever into the past, no tip, no beginning, turtles all the way down, you trade one agony for another. This is the dilemma cosmologists call the chicken and the egg problem, and Turok names it as the thing that drew him to this subject in the first place. If time is infinite into the past, then there is always a before, and you end up endlessly asking what came before that, and before that, and before that, with the explanation forever receding like a horizon you can never reach. An infinite past explains nothing. It just postpones the question infinitely. But a beginning, a first moment that seems to demand a cause outside the universe, outside physics, altogether. Either answer breaks the machinery of explanation. For a century, cosmology has been quietly impaled on this fork. There is, however, a third possibility, and noticing it was one of the great insights of 20th century cosmology. Perhaps what the universe needs at the beginning is not an infinite past and not an uncaused first event, but something humbler, a boundary condition, a rule about the edge. Here is the idea in everyday terms. Think of a violin string. The physics of the string, the tension, the density, the wave equation, does not by itself tell you what sound the string makes. You also need to know how the ends are held. Clamp both ends, and only certain notes are possible. The condition at the boundary is not an event that happened to the string. It is not something that occurred before the music. It is simply part of the specification of the system, as lawful as the wave equation itself. Now apply that thought to everything. What if the Big Bang is not an event that needs a cause, but a boundary, an edge of time whose condition is fixed by law? Then the regress stops, not because we found the first cause, but because the question of what came before dissolves, the way asking what is north of the North Pole dissolves. The laws that govern the universe's evolution would also govern its edge. Nothing outside would be needed. The universe would be, in Turok's word, minimal, a self-contained object, specified by its laws and its boundary, and by nothing else. This is not yet the mirror, but you can feel the shape of the door beginning to form. The question has sharpened from, why did the universe begin? A question that may have no scientific meaning to what is the boundary condition at the Big Bang, and that question is science. Different proposed boundary conditions make different predictions about the universe we can actually observe, about those 5 numbers we set on the table, about the static printed on the oldest light in the sky. Propose the wrong boundary, and the sky will contradict you. There is one more virtue of the boundary condition idea worth naming before we meet its champion, because it explains why serious physicists find it not merely convenient, but beautiful. It makes the universe explicable in the strongest possible sense. Hawking's analogy was thermal equilibrium. Put gas in a room, and you do not need to specify what each of the trillion molecules was doing at the start. The details wash out, and a handful of macroscopic quantities, temperature and pressure and volume, predict everything worth predicting. He dreamed of a cosmology like that. Specify the few, conserved, macroscopic facts about the universe. Impose a lawful condition at its edge. And everything else, the galaxies, the ripples, those 5 numbers on our table should follow as the most probable outcome, calculated rather than assumed. No divine adjustment, no arbitrary list of initial settings that might have been otherwise, no freedom for the universe to have begun any way but the way the laws demand. If that dream can be realized, then the beginning of the universe is not the least explained event in history. It is the most explained, the one event fixed entirely by law. One man understood all of this before almost anyone else. He had spent his career proving that the singularity was unavoidable, and he spent his final decades trying to tame the very monster he had certified. His proposal was beautiful. It was audacious. It involved bending the flow of time itself sideways into a direction no clock can follow. And it is the direct ancestor of the mirror, the idea whose magnificent failure showed Turok exactly where the truth might live. His name was Stephen Hawking, and the story of how his answer to the beginning of the universe rose, reigned, and quietly came apart is where we turn next. Stephen Hawking's proposal for the beginning of the universe is called the no-boundary proposal, and even people who believe it failed tend to describe it with a kind of reverence. To understand the mirror, you must first understand this idea, both why it was so seductive and precisely where it broke, because the mirror is, in a sense we will make exact, Hawking's dream repaired. Return to the cone, time runs up its side, space is the shrinking circle, at the bottom waits the sharp tip where the equations die. Hawking's thought was wonderfully geometrical. What if the problem is the sharpness? A sharp tip is a defect, a place where a shape fails to be smooth. But geometry knows how to fix that. Round it off. Replace the piercing point with a smooth closed dome. Think of the difference between the tip of a needle and the bottom of a wine glass, or better, the southern hemisphere of a globe. If the bottom of the universe were rounded like the bottom of a sphere, then there would be no special point at all. Trace your finger down the side of a rounded cone and past the bottom. The surface simply curves and comes back up. No edge, no tear. Every point near the bottom is as ordinary as every other point, exactly the way every point near the South Pole is ordinary snow and ice. The universe would have no beginning boundary, hence the name, and the question what happened at the first point would dissolve, because there would be no first point, just as there is no southernmost place south of the South Pole. But rounding the tip costs something, and the price Hawking paid is one of the most audacious moves in the history of physics. In real time, time as clocks measure it, the singularity theorems make the sharp tip mandatory. Hawking knew this better than anyone. He had proved it. The rounding is only possible if, near the bottom, time itself changes character. In the mathematics, this is done by letting time become what is called imaginary, a technical term from complex numbers, not a comment on its reality. What it means, in effect, is that close to the beginning, the equations are continued into a regime where time behaves like a fourth direction of space. Down there is no flow, no before and after, just 4 directions of a smooth, static geometry, a rounded dome on which nothing happens, because happening requires time, and time, in the ordinary sense, has not yet begun. Farther up the cone, the geometry transitions, and one of the 4 directions takes on the character we call time, and the universe as a story, events, causes, history switches on. You may feel a protest forming. Is that not just a trick? Perhaps. But notice what kind of trick it is. It is a candidate boundary condition, a precise, lawful specification of the edge of the universe, of exactly the kind we said the violin string needs. and it is arguably the most elegant boundary condition ever proposed. The condition that there is no boundary. The laws of physics would then govern not only the universe's evolution, but its origin, with no outside input, no arbitrary initial data, no divine adjustment. Hawking's ambition was for a universe that is, in the deepest sense, self-contained, a maximum likelihood universe, the most probable smooth cosmos, consistent with the laws themselves. Turok, who knew Hawking well and worked beside him, describes what he loved in the idea. You avoid the chicken and egg problem entirely. There is no infinite regress, because the past is finite. And there is no uncaused first event, because there is no first event, just a smooth dome where the questions run out. Turok was, in his own words, very taken with this idea. He did not admire it from a distance. He went inside it and worked on it for years, real years, the kind a scientist spends filling notebooks and chasing calculations that mostly fail. And it is exactly because he took the proposal that seriously that what he found carries weight. He found that it does not work. When you actually compute what kind of universe the no-boundary condition predicts, when you ask the rounded dome what should grow out of it, the answer comes back wrong, not subtly wrong. The proposal predicts an empty universe, a cosmos with the least possible amount of matter and radiation in it. The most probable universe, by Hawking's own rule, is one containing essentially nothing, no hot plasma, no seeds of galaxies, no you. Our universe, dense with radiation and matter and structure, is not what the smooth dome wants to make. A beautiful answer to the deepest question there is, and when you turn the crank, out comes a universe with nobody in it. Sit with the human weight of that for a moment. A man spends his final decades on a proposal meant to be his deepest legacy, deeper than black holes, deeper than the radiation that bears his name, and a colleague and friend who loved the idea spends years testing it, and the years return a verdict of empty. Turok does not tell this story with any triumph. When he speaks of Hawking, he speaks of courage. So much courage in one person, he says, is hard to conceive. There is a particular kind of grief that only exists in science. The grief of an idea too beautiful to be true, discovered to be exactly that, by the people who most wanted it to be true. But this is also precisely how science is supposed to hurt. An idea rigid enough to fail is worth 10,000 ideas flexible enough to survive anything. Hold on to that principle, because the rest of tonight runs on it. Now, why did the no-boundary proposal fail? This is where Turok's diagnosis becomes the hinge of our whole story. His conclusion, reached slowly, was that the deepest problem was not the dome itself. The problem was the setting Hawking placed it in. Hawking, like nearly everyone in the 1980s, embedded his proposal in the framework of cosmic inflation, and inflation, Turok argues, is where the rot lives. Inflation is the reigning theory of the universe's first instant. It proposes that in the first sliver of a second, space was dominated by a strange, hypothetical form of energy, inflationary energy, that drove expansion at a runaway, exponential rate, blowing up a patch of space, smaller than an atom, to cosmic size, in far less than a blink. The idea's appeal is real. Stretch a small patch violently enough, and you smooth it out, which would neatly explain why the universe today looks so uniform and so flat. But listen to how Turok describes the machinery, because his critique is the cleanest ever offered by an insider. You postulate a new form of energy, he says, and then you dial all of its properties so that the resulting universe fits the observations we see. The energy is carried by a hypothetical new field, and the field's behavior is set by a potential, a curve on a graph that a theorist is free to draw almost any way they please. Nothing anchors that curve. It is, in the jargon, a free function. Draw it one way, you get one universe. Draw it another way, you get another. And so, literally, you do not get any definite prediction. You get out what you put in. You get out what you put in. Keep that sentence. It is the epitaph of the adding era, and it will return tonight with its meaning turned inside out. The consequences of that freedom are exactly what you would expect. There are not one or two inflationary models. There are tens of thousands, each with its own hand-drawn curve, each fitting the same sky. And a framework that can fit anything, forfeits the thing that made physics physics. Compare, as Turok does, the theories we already trust. Maxwell's electromagnetism. No free functions. No dials, it predicts what it predicts. For every radio wave and every ray of light, and it has never once needed adjustment. Einstein's gravity, the same rigid honesty, tested from laboratory benches to colliding black holes. Against that standard, inflation is not a theory at all. It is a fit, a parameterization of our ignorance, wearing the costume of an explanation. And there was supposed to be a way to catch it one clean, smoking gun signature. Inflation's violent stretch should have shaken spacetime itself, filling the universe with long gravitational waves. And those waves should have left a visible imprint on the polarization of the oldest light in the sky. This is a real prediction, and to the field's credit, experimentalists have hunted it with heroic precision for decades. The simplest inflationary models predicted the imprint at a level of roughly 20% of the observed fluctuation signal. The measurements came back. Not there. The slightly less simple models said at least 10%. Not there. The observational ceiling has fallen to around 3%, and within the next few years it is expected to reach a fraction of 1%. The waves keep refusing to appear, and the models keep being revised downward to live under the shrinking ceiling, becoming, in Turok's words, more and more contrived and less compelling. You can always build another version. You will always be able to. That is precisely the indictment. So here is where half a century of cosmology stands. The most beautiful boundary condition ever proposed predicts an empty universe. The framework it leaned on predicts whatever you dial it to predict, and its one falsifiable signature is missing from the sky. A lesser scientist would conclude that the beginning of the universe is simply out of reach. Turok concluded something else, something almost insolent in its simplicity. Maybe the failure was never in the laws. Maybe it was in a single silent assumption everyone, Hawking included, carried down the cone without ever checking it, an assumption about size. Because there is a loophole at the bottom of the cone, it has been sitting in plain sight inside the equations. Physicists already trust the ones with no dials for 100 years. To see it, we have to ask what the universe's earliest contents actually cared about. And the strange, liberating answer is not size. Not size at all. There is a property hiding inside the oldest and most trusted equations in physics, and it is so quiet that you can work with those equations for years without ever noticing it. Maxwell's theory of electromagnetism, the theory of light itself, written down in the 1860s, does not care about size. Here is what that means, concretely. An X-ray is a wave of the electromagnetic field with a very short wavelength. Visible light is the same wave, longer. A radio wave is the same wave. Longer still, the span between crests might be a millimeter, or a meter, or a kilometer. Now, you might assume that somewhere in Maxwell's equations there is something that treats these differently, some scale that says this wavelength is special. There is not. Take any solution of Maxwell's equations and stretch it double every distance, or multiply it by 1,000,000, and you get another perfectly valid solution. The theory is invariant under changing scale. In a profound sense, nothing fundamental distinguishes an X-ray from a light wave from a radio wave. They are scaled up and scaled down versions of the same object. The theory of light has no ruler in it. And Maxwell's theory is not alone. The equation that governs the electron, Dirac's equation, one of the crown jewels of quantum theory, has the same silent property with one condition: the electron must be massless. Mass is what breaks the spell. Mass gives a particle a natural size, an inbuilt ruler, a scale it carries around like luggage. Strip the mass away, and Dirac's electrons become as scale-blind as Maxwell's light. Stretch the universe, shrink the universe. A massless particle cannot tell. Nothing in its equations references how big anything is. Now ask the question that changes everything. When does matter have no mass? The answer comes from one of the most beautiful discoveries of 20th century physics. Mass is not a possession, it is a circumstance. The particles of the Standard Model, electrons, quarks, all of them are not born with mass. They acquire it through their interaction with the Higgs field, And that arrangement is itself a consequence of symmetries being broken as the universe cools. In today's cold universe, the Higgs field has settled into its resting state, the symmetry is broken, and particles wade through the field and register mass. But wind the clock back, heat the universe. As temperatures climb beyond anything a star can produce, the broken symmetries mend. And in the earliest moments, the regime of the hot Big Bang, when the universe was a furnace of radiation at temperatures our largest colliders can only dream toward, matter was, for all practical purposes, massless. Every particle raced at or near the speed of light. Everything behaved like light. Put the two facts side by side and feel them click together. Fact 1. Massless physics does not care about size. Fact 2. At the Big Bang, everything was effectively massless. Conclusion. The contents of the infant universe could not tell how big the universe was. Stop and let that in, because it is the loophole the one Turok believes everyone marched straight past on their way down the cone. The horror of the singularity is a horror about size. Space shrinking to a point, distances going to zero, the universe becoming infinitely small. But small compared to what? Measured by whom? Size is not an absolute, it is a comparison, and a comparison requires a ruler, and a ruler requires mass. The photons streaming through the early universe carried no ruler. The effectively massless matter carried no ruler. A photon, Turok points out, cannot even tell whether the universe is expanding or contracting. You can predict how a Maxwell wave evolves without knowing anything about the size of the universe at all. So when our equations announce that near the beginning the universe becomes catastrophically small, they are reporting a fact about a quantity that nothing in that universe could measure, even in principle. What if the catastrophe at the Big Bang is not in the world? What if it is in the bookkeeping, a failure not of physics, but of the coordinates we chose to describe it? Physicists have been burned by exactly this mistake before, and the history is worth a moment, because it is the emotional template for everything that follows. Come stand at the North Pole for a minute. You are here with a map, a good map, the standard grid of latitude and longitude that has steered ships for centuries. And right here, at 90 degrees north, your map is having a breakdown. Every direction you face is south. The lines of longitude, which everywhere else on Earth run politely parallel, here converge into a single point beneath your boots at the pole. The map assigns this one spot every longitude at once, which is to say the longitude here is undefined, meaningless, singular. A navigator reading coordinates would conclude that something extraordinary happens at this place, some rupture in the world where east and west collapse into each other and the grid itself dies. Now look down, look at the actual ground, snow, wind, ice groaning softly as it drifts. The most ordinary place imaginable, flat, smooth, continuous in every direction, physically indistinguishable from any other patch of ice on the cap. Walk 20 paces in any direction, then look back. Nothing marks the spot. The catastrophe you read about was never here. It was on the paper. The world is smooth. The map has a singular point, because a sphere simply cannot be covered by that grid without the grid pinching somewhere. Choose different coordinates. Lay a simple square grid over the pole, and every point, including this one, becomes as unremarkable in the mathematics as it is under your feet. That is what a coordinate singularity is, a place where the description fails and the reality does not. And the 20th century learned, painfully, that Einstein's theory is full of such traps. The most famous is the edge of a black hole. When the first exact solution for a black hole was written down, the mathematics appeared to blow up at the event horizon. The metric of spacetime returned infinities there, and for decades, many physicists believed the horizon was a physical wall of some kind, a place where spacetime itself broke. It took nearly half a century to see the truth. In better coordinates, Kruskal coordinates, discovered in 1960, the horizon is revealed to be utterly smooth. An astronaut falling through it would notice nothing at that moment. No wall, no flash, no seam. The infinities had been artifacts of a poor choice of mathematical variables, a longitude at the pole mistake, wearing the costume of a catastrophe. Physicists had mistaken their map for the territory, and it cost them 50 years. So now return to the bottom of the cone and ask the forbidden question. The Big Bang singularity, the tearing off of the page, the mandatory catastrophe certified by the singularity theorems, is it the territory or is it the pole on somebody's map? Here is why the question suddenly has teeth. If the contents of the early universe truly do not care about scale, then a physicist is free to do something that sounds like cheating, but is mathematically honest. Change the ruler as you go. You are absolutely free, Turok says, to blow up the size of the universe by any amount you like, at any moment, because nothing physical is sensitive to it. No ruler exists down there to contradict you. So design your bookkeeping cleverly. As the universe shrinks toward the dreaded zero, rescale, stretch your coordinates so that, in the new ledger, the quantities that matter stay finite. The shrinking that terrified us was the one thing nothing in that universe could measure. Track only what the physics itself can feel, and you may find that the approach to the Big Bang is no more dramatic from the inside than the approach to the North Pole. Grid lines converging on a patch of perfectly smooth ice. Be careful, though, and be honest about what has and has not been said. A suggestive analogy is not a theorem. The singularity theorems are real mathematics, and they cannot be waved away with a story about maps. The escape only works if the scale blindness is exact where it needs to be, and if someone actually does the calculation, takes Einstein's equations, feeds them a universe full of radiation, chooses the clever ruler, and follows the solution all the way down to time zero to see with their own eyes whether it survives. An analogy invites, only a calculation decides, and there is one more reason to hold your breath. If the ice at the pole really is smooth, if the equations glide through the point where the universe's size reads zero without so much as a shudder, then the mathematics will not stop there. A smooth road does not end at a milepost. It continues. Something is on the other side. Turok and his collaborator Latham Boyle did the calculation. What they found on the far side of time zero is the reason this video exists. Before we cross, let us step back for a moment and put the pieces together, because we have been descending for a while now, and the air down here is thin. We began with a habit. For 50 years, physics answered every mystery by adding something new, and for the last 40 of those years, nothing new has shown up. We saw that the universe, measured honestly, is almost absurdly lean, the standard model plus 5 numbers, seeded with the simplest noise mathematics allows, tilted by 4%. We stood at the bottom of the cone, where Einstein's equations drive everything to a point and tear the page. And we met the two bad options that tear has always offered, an infinite regress of befores, or an uncaused first moment. We watched Hawking try to round off the tip with imaginary time, the most beautiful boundary condition ever proposed, and we watched it predict an empty universe, poisoned, in Turok's diagnosis, by inflation's dial-a-universe machinery, the framework that gets out only what you put in. And then we found the loophole. In the furnace of the beginning, everything was effectively massless, and massless physics carries no ruler. So the terrifying shrinkage toward zero size may be a fact about our map rather than the territory. A North Pole drawn on graph paper, a horizon-style illusion of bad coordinates. Everything from here forward stands on that one insight. The question stopped being, how do we escape the singularity? And became, is the singularity even there? Now for the calculation that answers it. In the late 2010s, Neil Turok and Latham Boyle, a theorist Turok worked with at the Perimeter Institute, and by Turok's account, the more fearless calculator of the pair, decided to do the simple thing that, remarkably, had never quite been done in this way. Take Einstein's equations. Feed them the most realistic, simple universe you can. One dominated by radiation, which is what the hot early cosmos actually was, a sea of light and effectively massless particles, the scale-blind contents we met in the last chapter. Add nothing. No inflationary field, no hand-drawn potential, no new ingredient of any kind. Then, using the freedom that scale blindness grants, choose the coordinates wisely, track the quantities the physics can actually feel rather than the raw size that nothing down there can measure, and follow the solution backward, not toward time zero, through it. What they found is the kind of result that makes a physicist put down their pen and stare. The solution does not break. Written in the right variables, the equations of a radiation-filled universe pass through the moment the size reads zero, without any breakdown at all, smoothly, in Turok's word, and he does not use such words casually. The Einstein equations, he says, do not see any problem at t equals zero. The point that 3 generations of physicists treated as the edge of law, the tear in the page, the place where explanation itself was disallowed. The equations glide across it, the way a well-chosen grid glides across the North Pole. This was a big surprise, Turok says, with the mildness of a man describing the moment the ground moved. Everyone had assumed the equations failed there. Nobody had checked, in these variables, whether the failure belonged to the universe or to the notation. And because a smooth road does not end at a milepost, there is more. Analytic is the mathematician's word for what the solution turned out to be at that point, and the word carries enormous weight, so let us give it 30 seconds of honest attention. An analytic function is one so perfectly well-behaved that its continuation is forced. Think of a straight line. If I show you the piece of it where x is positive and tell you the whole thing is a line, you know without any freedom, without any choice, exactly what it looks like where x is negative. There is one and only one way to extend it. That is the property Boyle and Turok found at time zero. The history of a radiation universe, followed down to the bang, does not merely survive the crossing. Its extension to the other side is unique. The mathematics does not ask you what you would like to be there. It tells you what is there. No dials, no free functions, no getting out what you put in. The equations that carried us down the cone continue themselves past the tip, and they hand you, whether you asked for it or not, a second half. So what is on the other side? Here is what the solution says. Read plainly. On the far side of time zero, there is another universe. It is not a different universe with different contents or different laws. The continuation is unique, remember. So everything about it is fixed by our side. It is a universe filled with the same radiation, governed by the same equations, expanding away from the same bang, but expanding in the opposite direction of time. From the perspective of anyone inside it, that universe would look forward in time toward the bang the way we look backward at it. Lay the whole object out, and it resembles 2 cones joined tip to tip, 2 expanding universes, sharing a single birth point, pointing away from each other in time. And the relationship between the 2 halves is not loose or approximate. The solution on the far side is, classically, the precise reflection of ours, the same universe, reversed, the way your reflection in still water is you, inverted. Boyle and Turok, following the mathematics to the place it had led them, found themselves writing down a sentence that sounds like poetry and is actually a boundary condition. Before the Big Bang, there is a mirror image of everything after it. It is worth being clear about what this is not, because the history of cosmology is crowded with ideas that sound superficially similar. This is not a bounce, in which an earlier universe collapses, crunches down, and rebounds outward into ours in a bounce. The other side is a past that caused us, an earlier chapter of one continuous story. The mirror is stranger than that. The other side does not precede us in any causal sense. It does not collapse into the bang and push through. Both halves expand away from the seam, and neither is the parent of the other. Nor is this a cycle, an endless wheel of universes, each giving birth to the next. There are exactly 2 sheets, 1 seam, 1 object, and nothing here was added to make it happen. That is the discipline this whole evening turns on. A bounce needs new physics at the crunch, some exotic mechanism to reverse a collapse at the moment the equations fail. The mirror needs only the equations themselves, read in the variables the early universe actually cares about, doing what analytic mathematics does, continuing, uniquely, because there is one and only one way to continue. Notice, before we go any further, what has already happened to the 2 ancient horrors of the beginning. The infinite regress is gone. There is no endless chain of befores, because the structure of time is not an infinite line trailing off into forever. It is finite and closed at the middle, a two-sided object with a seam, and the uncaused first event is gone too, because the bang is no longer an event in the usual sense, no more than the North Pole is an event on the Earth. It is the place where the coordinates meet, the seam where the two halves join, lawful all the way through, with the equations holding at every point, including the middle. Nothing began there. The object simply has that shape. Turok's own way of describing the discovery is disarmingly modest. We just followed the generic solution of the Einstein equations back to t equals 0, and out the other side, he says, and we found there is a whole class of solutions that are completely well-defined and just evolved through it, just followed the equations. No new fields, no new eras, no imaginary time, no rounding off. The most conservative act imaginable, trusting the 100-year-old theory a few steps further than anyone had dared. And the reward was an answer to the question, what came before the Big Bang, that no one had ever put on the table in quite this form. Not nothing, not turtles, a reflection. But now the hard questions arrive, and they arrive all at once. A classical solution is one thing, a principle is another. Why should the two halves match so perfectly? What precisely is reflected, just the direction of time, or more? Our universe is made of matter rather than antimatter. What is the mirror universe made of? And the question that will decide whether this is physics or metaphysics, is the other side real? Is there truly another cosmos back there, with its own galaxies, and perhaps its own puzzled inhabitants, wondering what came before their bang? Or is the mirror image something stranger and more subtle? A mathematical device whose job is to hold our universe's boundary in place, the way a reflection holds a pose without being a person. Turok has a very precise answer to that last question, and it may be the most philosophically loaded sentence in this entire theory. To get there, we need to look at the mirror properly, at what reflection means, when what is being reflected is everything. Come stand in a dark room for a moment. There is a tall mirror on the far wall, and you are holding a single candle. You lift it, and across the room, a figure lifts a candle in answer. You raise your right hand. The figure raises its left. You step forward. It steps forward to meet you. Everything about it is precise. The flame guttering in time with yours. The shadows sliding across its face as they slide across yours. And everything about it is reversed. Walk slowly toward the glass. The figure comes toward you at exactly your pace, feet meeting your feet, until the two of you stand a breath apart, and the two candle flames close on each other and touch at the surface. Right at the plane of the glass, where your world and that world meet, flame meets flame, hand meets hand, and neither ever crosses. The surface is the one place the two of you share. Now the question that matters, is there anyone over there? You know the answer. You have known it since childhood. There is no room behind the glass, no candle, no one walking toward you. The reflection is not a second person. It is something your world does at a boundary, a rule the light obeys at a surface. And yet, every prediction you could make about that figure, every flicker, every gesture, every photon, is exact. The reflection is not real, and it is not nothing. It is a perfect bookkeeping of a boundary. Hold that feeling. It is, almost line for line, the physics we are about to do. When Boyle and Turok found a mirrored universe on the far side of the bang, they faced a choice about what it meant. And here, they reached for one of the oldest, most trusted tools in mathematical physics, a technique that every physicist learns as a student, called the method of images. It goes back to the 19th century, and its home territory is exactly the scene you just stood in. Suppose you want to solve Maxwell's equations for light or electric fields in a room with a mirror on one wall. The direct way is to grind through the boundary, impose at the mirror's surface the conditions a conductor enforces, and solve the constrained equations. It works, but it is ugly. The elegant way is a trick of glorious effrontery. Delete the mirror. In its place, build a reflected copy of the entire room, every charge, every candle, every U reversed, on the other side of where the glass stood. Then solve the equations as if there were no boundary at all, in one big doubled room. The mathematics comes out identical. Every field, Every reflection you would ever measure in the real half is reproduced exactly. The image room enforces the boundary automatically by symmetry, and no physicist ever has believed the image room exists. It is a bookkeeping construction scaffolding you erect on the far side of a boundary so that the boundary takes care of itself. Now, transpose the whole scene from space to time. The Big Bang is the mirror. The universe before the bang is the image. Boyle and Turok's proposal, the CPT symmetric universe, published in 2018, is that the correct boundary condition at the beginning of time is precisely this. The bang is a surface of reflection, and the way to impose that mathematically is to place a reflected copy of our entire universe on the other side and solve the equations straight through, as if there were no boundary at all. The mirror universe plays exactly the role of the image room. It makes the boundary lawful, automatic, self-enforcing. In Turok's own words, the mirror image is just a trick for imposing a certain boundary condition at the Big Bang. And then, pressed on whether the universe before the bang is really out there, he gives the answer that carries his whole philosophy compressed into 3 sentences. Is there another person behind the mirror? No. The minimal picture of reality is that there is only one person. There is no one behind the mirror. Keep that sentence somewhere safe tonight. We will need it again before the end, and when it returns, it will mean more than it does now. But we owe the skeptic in you some precision, because Reflected is doing a lot of work in this story, and what exactly gets reversed is where the physics lives. When you looked in the glass, left and right traded places. When the universe reflects through the bang, 3 things trade places at once, and their names are C, P, and T. P is parity, the flip of space itself. Left-handedness for right-handedness, the mirror you already know. T is time reversal on the far side. Time runs toward the bang. From their perspective, the film played backward. And C is the strangest and most beautiful of the 3. Charge conjugation, the exchange of matter for antimatter. Every particle in our universe has a shadow twin with opposite charge. The electron has the positron, identical in mass, opposite in sign, and C swaps them. The universe, on the other side of the mirror, is not merely our cosmos rewound. It is reversed in space, reversed in time, and made of antimatter. Why those 3 together? Because of a theorem that sits at the very foundation of modern physics. You may remember from earlier tonight that the symmetries of nature are often broken. The Higgs breaks this one. The weak force violates that one. Nature, it turns out, violates C alone. It violates P alone, spectacularly. It even violates C and P together by a whisker. But the combination of all 3 C, then P, then T, applied at once, has never been observed to fail. Not once, in any experiment, anywhere. And there are profound mathematical reasons, woven into the marriage of quantum mechanics and relativity itself, to believe it cannot fail. CPT is widely held to be the one exact mirror nature possesses. So if the universe is going to reflect through its own beginning, this is the only mirror rigid enough to do it. Boyle and Turok did not select a convenient symmetry off the shelf. They reached for the single reflection that the laws of physics are believed to enforce without exception, and proposed that the universe as a whole, not just its particles, but its entire history respects it. The universe before the bang is our CPT image, an anti-universe, spatially flipped, running the other way in time. The whole two-sided object is CPT symmetric about the bang, which means the most fundamental symmetry of the laws is also the shape of the cosmos itself. And now comes the discovery. Inside the discovery, the point where this stops being an elegant reinterpretation and becomes an explanation. Ask a childlike question. Fine. If the universe is a two-sided object, why should there be a bang in the middle at all? Why should the two halves meet at a point of zero size, rather than joining side by side like 2 pages lying flat? Boyle and Turok asked exactly this, and the answer stopped them cold. Try to build the two-sided universe with the trivial identification, glue each moment to its counterpart, without any flip, no reversal, nothing, and the construction collapses. The two surfaces simply coincide. The same universe pasted onto itself. No interpolation, No history, nothing new. But glue them with the CPT, twist the honest mirror, space flipped, time reversed, and the mathematics is forced to thread the join through a point where the scale of the universe goes to zero, forced. The two halves cannot be sewn together with a twist unless the seam pinches. In other words, given this boundary condition, there had to be a Big Bang. The most violent fact in the history of existence, the thing every cosmology has treated as an inexplicable given. The brute event, demanding a cause, falls out as a topological necessity, a consequence of how a twisted object must close. A Mobius strip must have a twist somewhere. A CPT symmetric universe must have a bang. The question, why did the Big Bang happen? The question that has defeated every philosophy and every physics since humans first asked, it receives, for the first time, an answer of the form, because the shape of reality requires one. Feel what has shifted tonight. When we stood at the bottom of the cone an hour ago, the bang was a wound, a tear in the page, an edge where explanation was disallowed, flanked by two unacceptable infinities. Now look at it. The tear has become a seam. The wound has become the one place where the two halves of a perfectly symmetric object touch flame, meeting flame at the surface of the glass. Nothing exploded. Nothing began, in the sense of an uncaused event. The universe, this picture says, is a single finished shape whose deepest symmetry demands a waist at its middle, and we live in one half of it, looking back at the mirror and calling it the beginning of time. And yet the reflection in your dark room did one more thing, if you remember. It did not just stand there. When you walked backward through the evening of your life, it walked forward. There is an arrow in this story, the oldest arrow there is, the one that points from your childhood to this bed, from causes to effects, from past to future. Our universe runs one way. The image universe runs the other, which raises a question this theory is uniquely equipped to answer, and which no theory before it has answered without embarrassment. Why does time have a direction at all? For that, we need to visit a room full of air, and a lonely genius from the 19th century who worked out what time's arrow is made of, and paid for the knowledge with his peace of mind. The direction of time is the most familiar fact in your life, and it may be the least explained fact in all of physics. Eggs break and do not unbreak. Coffee cools and does not unheat itself. You remember last summer and not next summer. Every clock, every heartbeat, every memory points the same way, so uniformly that the pointing feels like a law of nature. Here is the scandal. It is not. Look into the fundamental equations, Newton's mechanics, Maxwell's light, Einstein's gravity, the quantum theory itself, and you will find no arrow anywhere. Every one of those laws works identically backward and forward. Film any collision of particles and play the film in reverse, and the reversed film shows a process that obeys the laws just as perfectly. The microscopic world is even-handed about time to an almost perverse degree, and yet the macroscopic world, the world of eggs and coffee and you, is a one-way street. Where does the arrow come from if the laws underneath have none? The first person to see to the bottom of this question was Ludwig Boltzmann, a physicist working in Vienna in the late 1800s, decades before anyone knew the universe had a beginning. Boltzmann understood that the arrow is not written in the laws. It is written in the odds. Disorder has more ways to exist than order, and that lopsided arithmetic is nearly the whole story. A broken egg is not more lawful than an intact one. It is more numerous, and there are unimaginably many more ways for shell and yolk to be scattered than to be assembled. Systems drift from rare arrangements toward common ones. For the same reason, a shuffled deck almost never comes out sorted, not because sorting is forbidden, but because sorted hands are outnumbered beyond reckoning. Time's arrow, Boltzmann saw, is probability wearing a costume, but that insight, brilliant as it is, only relocates the mystery. If disorder is overwhelmingly probable, the deepest question becomes, why was there ever order to lose? Why did the universe start in the rarest of arrangements, wound up like a clock, low in entropy, dense with unspent order that has been cascading downhill ever since, through stars, through sunlight, through you when nearly every possible arrangement is disorderly? Saying the universe runs down because it started wound up merely moves the question to who or what wound it. By the logic of probabilities, the wound-up beginning is the least likely thing that could have happened. The arrow of time, traced honestly to its source, becomes the puzzle of the improbable beginning. Boltzmann knew this, and his attempt to answer it produced one of the strangest, most haunting thought experiments ever devised. Picture a sealed room full of air. Nothing enters, nothing leaves. The molecules jitter and collide by the trillion, evenly spread, at equilibrium maximum disorder, nothing happening, forever. Now grant yourself a lifespan beyond all meaning, and simply watch, for ages beyond ages, nothing, uniform grey equilibrium. But the molecules never stop shuffling, and given enough time, every arrangement, every one, however absurd, eventually gets its turn. So you wait, and epochs pass that make the age of our universe look like a blink, and then one afternoon, with no cause and no warning, it happens. The air begins to gather. Molecule by molecule, collision by blameless collision, the room empties itself toward one corner, a wind with no source, a tide with no moon, until the whole atmosphere of the room stands crowded into a single glittering cubic foot, and for one impossible instant there is perfect order where no order should be. Then it lets go. The air rushes out, fills the room, and the long grey equilibrium resumes as if nothing had occurred. Now the question Boltzmann asks you, suppose a tiny observer lived through the gathering phase, watching air organize itself, watching disorder decrease everywhere, effects preceding their causes. What would that observer conclude? That time was running backward, and an observer, in the rushing out phase, would see a young, wound-up world unwinding, a world just like ours, same room, same laws. The direction of time is not in either half. It is in which side of the corner you are standing on. That is the thought Boltzmann left the world. The arrow of time points away from the improbable moment. Wherever a system finds itself near a state of rare, concentrated order, the direction of increasing disorder becomes the future, automatically, on both sides. Time's arrow is not a rail the universe rides. It is a slope, and a slope runs downhill in both directions from a peak. Boltzmann's own version of the idea had a fatal flaw. He needed the ordered moment to arise by pure luck, and pure luck, at that magnitude, is a non-answer. An accident enormous enough to wind up an entire universe is precisely as improbable as the wound-up universe it was invoked to explain. You have purchased nothing. His century abandoned the idea, and Boltzmann's story ended in tragedy, but the shape of his thought survived, waiting for a mechanism, waiting, as it turns out, for a mirror. Because look at what the two-sided universe has been quietly assembling behind our backs. Boltzmann needed a special moment of extraordinary order, flanked on both sides by histories running away from it. He could only get one by accident. Boyle and Turok get one by necessity. The CPT twist, remember, forces the two halves of the universe to meet at a pinch, a seam of zero size, which is automatically a state of extreme compression and extraordinary order. The wound-up mainspring to end all mainsprings. Nothing lucky about it. The topology demands the peak. And on either side of that peak, precisely as in Boltzmann's room, a universe unwinds, disorder growing, structure cascading, entropy climbing, with each half experiencing time as flowing away from the middle. Ask someone in our half where the past is, and they point at the bang. Ask someone in the mirror half, and they point at the bang too. Both arrows point outward, back to back, like two rivers rising from the same mountain ridge and flowing down opposite slopes. Neither direction is the true one. The two-sided universe as a whole has no arrow at all. Turn the entire object upside down, like an hourglass, and by its CPT symmetry, it is indistinguishable from itself. The arrow you have trusted every day of your life is real, but it is local. It is your half slope. Time does not flow through the universe. The universe has a shape, and you are sliding down one side of it. Notice what this explanation costs. Nothing. No new field was hired to break time's symmetry. No special initial condition was written in by hand. The improbable beginning that has embarrassed physics since Boltzmann, the wound-up clock nobody could account for, is supplied free of charge by the same boundary condition that dissolved the singularity and necessitated the bang. One idea, 3 ancient debts paid. And Turok suspects the arrow may settle other accounts too. He points at the measurement problem of quantum mechanics, the notorious puzzle of why observations have definite outcomes, why the wave function seems to commit itself when measured. Notice, he says, that measurement is the one place where an arrow intrudes into quantum theory. Before the measurement, you do not know. After, you do. A before and an after, in a theory whose equations otherwise flow both ways. If the cosmological arrow comes from the mirror's geometry, then perhaps the arrow inside the laboratory does too. Perhaps the direction in which wave functions commit is, at bottom, the same slope you are sliding down. He offers this as suspicion, not result, and we will let it stand as exactly that. Be careful, as always, about what has actually been established. The mirror explains why an arrow exists on each side of the bang. The detailed accounting of our particular universe's order, every step from the seam's compression to the wound spring of stars and life, is a program of work, not a finished ledger, and honest physicists will argue about pieces of it for years. But the shape of the answer is unlike anything that came before. For a century, the arrow of time has been an orphan, an everyday absolute with no parent among the laws. Tonight it has a candidate parent, a geometry, a twist, a peak from which both futures descend. So the ledger of the mirror now reads, singularity dissolved, the bang necessitated, the arrow of time explained. It is a remarkable run. And it is all, so far, gravity and geometry, the grand architecture of spacetime, the part of the story Einstein's equations were always going to dominate. But a universe is more than its architecture. It is filled with something, fields, particles, matter, light, the quantum world, with its own strangeness and its own bookkeeping. And it is there, in the small print of the quantum vacuum, that this theory faces its most dangerous test. Because empty space, according to quantum field theory, is not empty, it seethes. And when physicists add up what the seething should weigh, they get the single most catastrophic wrong answer in the history of science, a mistake so large it should have crushed the universe in its first instant. Any theory that claims to explain everything with nothing new must walk into that furnace next. So that is where we go, into the vacuum itself, to meet the infinity that lives in empty space. Take away everything, every particle, every atom, every photon of light, sweep a region of space perfectly clean, chill it to absolute zero, shield it from the entire universe, and ask what remains. The common sense answer is nothing. The quantum answer is almost everything. This is one of the deepest lessons of 20th century physics, and it comes straight out of the framework that underwrites every electronic device you own. In quantum field theory, the fundamental objects of reality are not particles, but fields continuous, space-filling entities, like the electromagnetic field, which has a value at every point in space, at every moment. Particles are ripples in these fields, little traveling packets of excitation. A photon is a quantized ripple of the electromagnetic field, an electron, a ripple of the electron field. And here is the crucial point. A quantum field cannot hold still. The same uncertainty principle that forbids an electron from having a definite position and a definite speed at once forbids a field from sitting quietly at zero. Even in a perfect vacuum, every field at every point trembles. Physicists call these zero-point fluctuations a ceaseless, microscopic shimmer that no cooling, no shielding, no emptiness can switch off. The vacuum is not the absence of everything. It is every field in the universe, idling. This is not speculation. The trembling has measurable consequences, fingerprints on atomic energy levels and on forces between metal plates that experiments have confirmed again and again. The vacuum shimmer is as real as sunlight, which makes what comes next one of the most humiliating episodes in the history of physics. Ask an innocent question. How much energy does the trembling contain? Every jitter of every field carries a little energy, and empty space extends in every direction, and the fields can tremble at every possible wavelength, from lazy undulations to ripples finer than any atom. Add it all up. The sum does not converge to some small, tidy number. It diverges. The calculation returns infinity, an infinite energy density in every cubic centimeter of empty space. And it gets worse, in a way that will matter enormously in a few minutes. The fields of nature come in two great families: bosons, the force carriers like the photon, and fermions, the matter particles like electrons and quarks. When you do the accounting, a beautiful and ominous pattern emerges. Bosons contribute positive infinity to the vacuum's energy, while fermions contribute negative infinity. The two families pull in opposite directions. And because the standard model happens to contain more fermion fields than boson fields, the naive grand total for the energy of empty space comes out not just infinite, but negatively infinite. According to our best theory of matter, taken at face value, nothing weighs less than negative infinity. For decades, physicists lived with this absurdity through a strategy that is equal parts brilliant and embarrassing. They agreed not to look, and they had a real excuse, which is worth understanding. In every laboratory experiment ever performed, only energy differences matter. If the vacuum carries some enormous, constant baseline of energy, every measurement subtracts it automatically. You see only the excess above the vacuum, the way you can weigh cargo without ever knowing the weight of the ship. So the infinite baseline, however grotesque, was invisible, and the technique for hiding it, called renormalization, was refined into one of the most precise calculating tools in science. Subtract the infinity once, consistently, and everything on top of it comes out right to 9 or 10 decimal places. It works magnificently. It also, as Turok emphasizes with unusual bluntness, buys its magnificence at a price. This process leaves you with very little understanding of what is actually going on in the vacuum, because you have just subtracted it away. Renormalization is not an explanation of the vacuum. It is a decision, institutionalized across 3 generations of physicists, to change the subject. But there is one force that refuses to change the subject: gravity. Because gravity, uniquely, does not respond to energy differences. Einstein's equations couple gravity to the total energy every joule, everywhere, including the baseline. Gravity weighs the ship. The moment you place quantum field theory in the presence of gravity, the vacuum's ledger is torn open and its infinite contents spill directly into the curvature of spacetime. Feed a negatively infinite vacuum energy into Einstein's equations, and the prediction is unambiguous. Spacetime should convulse. The universe should recollapse in about a Planck time, 10 to the minus 43 seconds, curling up and annihilating itself in the first instant. You would get garbage, Turok says, and the universe would be over before it began. Instead, the universe is here, 14 billion years old, serenely expanding, and here is the twist of the knife. We have measured what empty space actually weighs. That measurement is the cosmological constant, the first of our 5 numbers read from the accelerating expansion by watching distant exploding stars across billions of light years. The measured value is not 0. It is tiny positive, and so small that its natural expression carries roughly 120 zeros between the decimal point and the first significant digit when written in fundamental units. Compare. The theory of the quantum vacuum, taken naively, says infinity. Refined estimates that cut the sum off at the limits of known physics say a number about 10 to the 120 times larger than what is observed. A 1 followed by 120 zeros. It is routinely called the worst theoretical prediction in the history of science, and the description is not hyperbole. There is no second-place error within shouting distance, anywhere, in any field. Somehow, the seething, infinitely energetic vacuum of quantum field theory presents itself to gravity as almost, but crucially, not exactly nothing. Some conspiracy of cancellations, operating to 120 decimal places, is quietly balancing the books of empty space, and no one has ever identified the accountant. And the vacuum's misbehavior does not stop at its weight. There is a second casualty, subtler, and for our story tonight, even more consequential. Remember the hero of the crossing, the scale symmetry of Maxwell's light and massless matter, the size blindness that let the equations glide through the bang like a grid over the North Pole. The entire passage through time zero was underwritten by that symmetry. Here is the dreadful footnote the vacuum adds. When quantum fluctuations are handled by the standard renormalization procedure, that very symmetry gets damaged in the process. The bookkeeping that hides the vacuum's infinite energy also, as a side effect, breaks the scale invariance of the quantum theory physicists call the injuries trace anomalies, or Weyl anomalies. After the mathematician Hermann Weyl, who first understood such symmetries, the word anomaly here has a precise, tragic meaning, a symmetry that the classical equations possess perfectly, but that no consistent quantum treatment seems able to preserve. So the doorway we walked through 2 chapters ago, the scale-blind bang, the smooth seam of the mirror, was a doorway certified by classical physics. Quantum physics, as usually handled, defaces exactly the symmetry that held the door open. If the mirror universe is to survive contact with the quantum world, the anomalies cannot merely be regretted. They must be cancelled, erased exactly, to the last decimal place, by something already in the theory, or something so minimal it barely counts as an addition. So take stock of the crisis, because this is the deepest debt on the books, and every theory of everything must pay it or die. Empty space, by the plain arithmetic of quantum field theory, should weigh negative infinity and should have crushed the cosmos at birth. Instead, it weighs a whisper more than nothing. The symmetry that makes the Big Bang passable is broken by the very procedure invented to manage the vacuum's excesses. And the establishment's 2 grand responses over 50 years have been, first, renormalization, the disciplined art of not looking, and second, the adding era's solution, supersymmetry, which proposed to cancel the vacuum energy by doubling the universe's particle inventory, boson for fermion, a beautiful balancing that experiment has now largely dismantled. The infinity remains. The anomalies remain. The accountant remains unidentified. Now recall the wager this entire evening rides on. Nothing new. Turok's extreme minimalism forbids the standard escape routes, no supersymmetric doubling, no new energy fields, no invented machinery. Whatever balances the books of empty space must be found within a hair's breadth of the physics we already possess, or the mirror universe joins Hawking's dome in the Museum of Beautiful Failures. It seems impossible. The vacuum owes infinity. The minimalist's wallet is, by design, nearly empty. And yet, in the 1950s, one of the founders of quantum mechanics toyed with a strange class of fields with a property so peculiar that they contribute to the vacuum while refusing to be particles at all. Fields that could, in principle, sit in empty space and cancel debts without ever once showing up in a detector. For half a century, they were a curiosity, a footnote in the mathematics. When Boyle and Turok went looking for the vacuum's accountant with minimalist constraints, the trail led them there, and then the mathematics did something no one expected. It answered a question they had not asked. It told them how many fields it needed, 36, and hidden inside that number was the answer to a mystery physics had carried, unsolved, since 1936. Why the universe's parts list is printed in triplicate. Werner Heisenberg spent the 1950s chasing a theory of the strong nuclear force, and along the way he played with a mathematical object so strange that the mainstream set it aside for half a century. It was a field, a space-filling entity like all the others, but a field with no dimension. That phrase needs unpacking, because it is the key to everything in this chapter. Every ordinary field, in physics, carries what physicists call a mass dimension, loosely, a built-in relationship to scale, a sensitivity to the size of things, the same luggage that mass itself brings. The Higgs field has it, the electromagnetic field has it, but one can write down fields that have none, dimension zero fields, quantities more like an angle than a length. An angle is a pure number. 30 degrees is 30 degrees, whether it is drawn on a coin or across a galaxy, and a dimension zero field is similarly indifferent to scale, unchanged when the universe is stretched or shrunk. You may already hear the resonance. Everything about the mirror universe has turned on scale blindness, on physics that does not care about size. These fields are scale blindness incarnate. They carry the symmetry of the bang in their very definition. they have a second strangeness. Their equations of motion involve 4 derivatives, rather than the customary 2, a mathematical structure physicists have distrusted since the 19th century, when it was shown that such theories, treated classically, can run away catastrophically, their energy unbounded below. That distrust is why the fields sat in the drawer for 50 years. But Boyle and Turok, examining the quantum version carefully, found the standard doom does not straightforwardly apply. The quantized theory states all carry positive energy. The genuine oddity lives elsewhere. Some of the quantum states carry negative probabilities, a pathology that would be fatal in a theory of particles, because a particle you detect minus 30% of the time is nonsense. The resolution is the strangest and most elegant fact about these fields. When you restrict attention to the healthy states, the ones with sensible probabilities, as physicists routinely must do in the mathematics of the known forces you find, the healthy sector contains almost nothing. For these fields, only the vacuum survives the cut. They permit no particles whatsoever. A dimension 0 field fills all of space, contributes to the energy and structure of the vacuum, and yet can never not at any energy, not in any collider, not in principle show up as a detectable particle. It is a field whose entire existence is bookkeeping in empty space. Now, you could hardly design a stranger job applicant, but read the job description we wrote at the end of the last chapter. Wanted something to balance the infinite books of the vacuum, must cancel an infinite negative energy, must repair the broken scale symmetry, the trace anomalies, must add no new particles to the world, because after 50 years, the detectors have made it clear there are none to find. The dimension 0 fields are not merely a candidate. They are practically the only candidate, contributors to the vacuum, carriers of exact scale symmetry, constitutionally incapable of being particles, where every previous repair to the vacuum supersymmetry, above all, tried to cancel infinities by doubling the visible world. These fields cancel without appearing. Minimalism's accountant, if it exists, looks exactly like this. So Boyle and Turok posed the precise question. Take the standard model, coupled to gravity. Tally its 3 fatal vacuum debts, the infinite 0-point energy, and the 2 independent trace anomalies that damage scale symmetry. Ask, what is the smallest number of dimension 0 fields whose contributions cancel all 3 debts simultaneously, not approximately, but exactly, the way only symmetry can cancel? This is not a curve to be fitted. It is arithmetic with one honest answer, and the answer that fell out of the calculation was 36. Add exactly 36 dimension 0 fields to the standard model, and the vacuum energy cancels, both anomalies cancel, and the scale symmetry that holds open the door at the bang survives quantization. 35 fails, 37 fails. 36 keys, cut to fit 3 locks at once. If that were the whole story, an honest skeptic would call it numerology. Turok himself, disarmingly, uses that very word for this first step. 1 tuned integer, 3 debts paid, suggestive, but a mind primed for patterns can find integers anywhere. What elevates the number is what it did next, unasked. 36 is divisible in a particular way, and when Boyle and Turok examined how the cancellation actually distributes itself across the mathematics, they found it interlocks with the fermion content of the standard model itself. The cancellation goes through only if the matter fields of the universe come in exactly 3 copies, 3 generations, and only if each generation carries 1 additional member. A right-handed neutrino, a particle long suspected on independent grounds, but never yet observed. Sit with what that means. The triplication of matter, the fact that nature built the electron, then built the muon and the tau, as heavier duplicates nobody ordered, the mystery that made a Nobel laureate famously ask, "Who ordered that?" has stood unexplained since 1936, a brute fact filed under decoration. In this framework, it stops being decoration. 3 generations are load-bearing. Remove 1, add 1, and the vacuum's books no longer balance. The universe, in effect, must print its parts list in triplicate, or the whole ledger of empty space collapses. For the first time in 90 years, someone has offered a reason for the copies, and it fell out of a calculation aimed at something else entirely. You get out what you put in. That was the curse we carved over the door of the adding era, Turok's epitaph for inflation and everything like it. Look what has happened to it here. Boyle and Turok put in one demand: balance the vacuum with the least possible machinery. Out came the number 36. Out came 3 generations. Out came right-handed neutrinos hold that name. It returns in the next chapter with a starring role. For the first time in this long story, a theory has handed back more than was fed into it. The curse has been inverted. They got out more than they put in. And the fields were still not finished. Because there remained the 2 most public debts on the entire ledger, the 4th and 5th of our 5 numbers, the fingerprints on the oldest light in the sky, the strength of the primordial ripples, 1 part in 10,000, and their tilt 4%. Inflation was invented, above all, to account for those ripples, and it accounts for them the way a tailor accounts for a fit by adjustment, after the fact, with a hand-drawn curve. The dimension 0 fields permit no adjustment. They are rigid, no potential to sculpt, no dials, no free functions, nothing about them can be tuned, which means that whatever pattern of vacuum trembling they imprint on the newborn universe is not a fit, but a verdict. So Boyle and Turok computed the verdict. The fluctuations these fields generate through the mirror symmetric bang came out Gaussian, the simplest noise, exactly as the sky shows. They came out scale invariant, with a small tilt exactly the shape the sky shows. And the amplitude and the tilt, in this framework, tie back not to any new invented quantity, but to measured constants of the standard model itself. The calculation reaches into known physics, the strength of the strong nuclear force among the inputs, and returns the numbers on the sky. 1 part in 10,000, a tilt of about 4%. The fingerprint you were asked to remember at the start of tonight, the 4% lean in the universe's opening static, traced, if this framework is right, to the trembling of 36 silent fields, keeping the books of empty space at the moment of the mirror. Turok reports all of this with a candor that is worth quoting in spirit. We got much more than we bargained for, he says, and, in the same breath, this is a first hint. I cannot claim it is done and dusted. The calculations so far are leading order first approximations, with simplifying assumptions that must be justified, refined, attacked. The negative probability sector must be policed with complete rigor. Of the 5 numbers on our table, honesty requires the ledger read out precisely. The amplitude and the tilt are claimed as genuine explanations. The other 3, the cosmological constant's exact value, the dark matter density, the matter-to-light ratio are still fitted, though fitted with remarkably little. The framework explains why the vacuum energy should be small and positive without yet predicting its value, and the other 2 are set by parameters native to the standard model, with right-handed neutrinos, not by invented fields. Partial payment, openly declared. But compare the accounting standards. Inflation fits the fluctuations with a free function, an infinity of adjustability. This framework confronts them with none. A theory with no dials that lands within reach of the right answers, on its first pass, deserves something rare in modern cosmology, the risk of being checked. And it can be checked. That is the astonishing thing. After 50 years of theories that retreated beyond every horizon of measurement, this one walks toward the instruments. It stakes its life on a number that will be measured within a few years by telescopes that are already built, mapping the sky right now. The wager runs through the lightest, shyest, most ghostly particle in all of nature. The mirror universe is about to bet everything on the neutrino. Every second of your life, about 100 trillion neutrinos pass through your body. They are passing through you now, in the dark, streaming up from the sun, through the entire thickness of the Earth, as if the planet were fog. Neutrinos are the most antisocial particles in the known universe. No electric charge, no color charge, almost no mass, interacting so feebly that a wall of lead 1 light-year thick would stop only about half of them. And yet this ghost, of all particles, is where the mirror universe has chosen to stake its life. To see why, we need one last piece of the standard model's small print, and it is a piece with a hole in it. Particles like electrons and quarks come, in the language of physics, in two mirror versions of themselves, left-handed and right-handed, a label describing how a particle's internal spin relates to its direction of motion. Every charged particle of matter has both versions. Nature uses the two differently. The weak force, bizarrely, talks only to the left-handed ones, but both exist. Except in one case, the neutrino. In the standard model, as written, the neutrino appears only in its left-handed version. The right-handed neutrino is simply absent from the table, a missing chair, at an otherwise symmetric banquet. For decades, that absence could be shrugged off, because a right-handed neutrino would be the single most invisible object in particle physics. No charge of any kind, blind even to the weak force coupled to the rest of reality, essentially through gravity alone. If it existed, you would expect never to have seen it, and then nature tipped its hand. Neutrinos, it turns out, have mass tiny, but real. The experiments that prove they oscillate between types settled that beyond doubt, and massless particles cannot do what they were seen doing. Here is the rub. In the minimal standard model, the neutrino cannot have mass without help. The simplest, oldest, most economical way to give it one known since the 1970s as the seesaw mechanism is to fill the empty chair, admit right-handed neutrinos, make them extremely heavy, and the arithmetic does the rest. A seesaw needs two ends. The heavier the hidden right-handed partner, the lighter the visible left-handed one. Push one side up by a mountain, and the other side settles down to a whisper. Make the right-handed neutrinos heavy beyond any accelerator's reach, 10 billion times the proton's mass, and up, and the observed, almost nothing masses of the familiar neutrinos come out naturally. Now watch three storylines converge. The neutrino experiments say the chair should be filled. The seesaw says its occupant is enormously heavy and essentially invisible. And the 36 fields, remember the gift from the last chapter, demand the chair be filled. The vacuum cancellation goes through only with 3 generations, each carrying a right-handed neutrino. The mirror universe does not merely tolerate these particles. It requires them. So it is fair to ask what such a particle would be like, heavy as a dust mote of pure mass, touching the world through gravity and nothing else, drifting through galaxies without ever colliding, without ever shining, without ever announcing itself. Sit with that description for a moment. Massive, invisible, feels, gravity, and nothing else. You have heard this description before. A quarter of the universe answers to it. It is dark matter, item 2, on our list of 5 numbers. The unseen 5/6 of all matter, whose gravity holds every galaxy together, whose identity has been hunted for 40 years through colliders and underground vats of frozen xenon, all silent. The mirror universe's answer has been sitting in the empty chair all along. The dark matter is the heaviest right-handed neutrino, a particle the theory was forced to include for entirely separate reasons, whose defining property is precisely the perfect silence that 40 years of detectors have reported. But an identification is cheap unless you can do arithmetic with it, and here the mirror performs its most distinctive trick. For any dark matter candidate, the make-or-break question is abundance. Why is there exactly as much of it as we observe 5 parts dark to 1 part ordinary? For most candidates, the answer is negotiated through adjustable interactions. The right-handed neutrino allows no negotiation. It interacts too feebly for any of the usual production stories. Boyle, Turok, and their colleague Kieran Finn realized the mirror itself does the producing. Quantum field theory. On the doubled, CPT symmetric spacetime, 2 universes joined at the seam, fixes how many right-handed neutrinos the expanding geometry itself conjures into being, with no dials to turn. Gravitational production. Computed across the mirror boundary condition. They ran the calculation, and the abundance came out about right. The observed dark matter density, from a particle nobody can detect, produced by the shape of the beginning itself. Once again, more out than in. And then the theory did the bravest thing a theory can do. It signed its own death warrant and post-dated it. Follow the logic. It is short and merciless. For the heaviest right-handed neutrino to be the dark matter, It must be stable. It must have survived 14 billion years without decaying. The seesaw, however, works by mixing right-handed and left-handed neutrinos. That very mixing would let the heavy one decay. So for the dark matter candidate to survive, its mixing must be exactly zero, its channel to the seesaw switched off entirely. But the seesaw is what generates the light neutrino masses, and if one of the three heavy partners sits out, the arithmetic loses a term, and one light neutrino goes without. The lightest neutrino must be exactly massless. Not nearly massless, exactly. That is not a preference or a tendency. It is a rigid consequence, a number nailed to the wall in advance. If the lightest neutrino has any mass at all, the heavy partner decays, the dark matter identification collapses, and the mirror universe, this entire beautiful structure we have spent the night assembling, is wrong. Here is what makes that sentence electric rather than academic. The measurement is coming, and soon. Neutrino oscillation experiments have already fixed the differences between the three masses. What no one yet knows is the absolute flaw. The answer, remarkably, will come not from particle physics, but from the sky, from cosmology itself. Neutrinos, outnumbering atoms in the universe by billions to one, collectively tug on the growth of cosmic structure. The heavier they are, the more they smear out the formation of galaxies, and so the pattern of galaxies encodes the sum of the three masses. A new generation of galaxy surveys is reading that pattern now. Ground-based instruments mapping tens of millions of galaxies have already pushed the allowed sum down toward the minimum that the oscillation data permit, and a space telescope named Euclid, launched in 2023 and surveying a third of the entire sky, is expected within a few years to pin the sum so precisely that the mass of the lightest neutrino will be cornered at a confidence approaching the 5 sigma standard physics reserves for the word discovery. If the answer is massless, the mirror universe survives its first trial by fire, and one of its strangest predictions becomes one of its proudest credentials. If the answer is anything else, Turok loses, and he says so plainly. There is a second, slower jury as well. If neutrinos take their masses this way, a rare process called neutrinoless double beta decay must occur 2 neutrons in a nucleus decaying in unison, with the neutrinos cancelling out of the transaction entirely. Underground experiments on several continents are watching tons of ultra-pure crystal and liquid for exactly this signature. The predicted rate is tiny, and the verdict may take a decade or two. Falsifiable twice over, on a schedule, in public, after 5 decades of frameworks that could survive any observation, it is worth pausing to notice how rare that sentence has become. The same insistence on testability is pushing the program outward, past the bang, toward the other great singularity, the one inside black holes. This work is young and partly unpublished, so hold it lightly, as Turok does. The interior singularity of a black hole, unlike the bang, is genuinely pathological, not analytic, not smooth in any coordinates, a place where the equations truly fail rather than merely appearing to. Turok's response is characteristically radical. Perhaps, then, it is not a solution at all. Perhaps histories that end on such singularities are simply illegitimate, forbidden from the quantum sum, and the true story of a black hole is a subtler, analytic history in which infalling matter passes through a profoundly quantum region near the horizon, cousin to the mathematics of quantum tunneling, where particles traverse classically impossible barriers by borrowing complex, imaginary paths and ultimately returns as the Hawking radiation that evaporating black holes emit. In such a picture, nothing ever truly hits a singularity. Time never ends inside a black hole. It makes no sense quantum mechanically for time to end. Turok insists, and the century-old paradoxes of information loss dissolve. If that program succeeds, it will make predictions about the horizons we have now begun to photograph and the gravitational waves we now routinely hear. It is the same single conviction, applied without exception. The laws we have do not fail, only our descriptions do. So the mirror universe now stands fully assembled before you, singularity dissolved, bang necessitated, arrow explained, vacuum balanced, generations counted, dark matter named, executioner scheduled. One question remains, and it is the question the whole night has been climbing toward. Could we ever see it? Not infer it, not fit it, see it, catch a signal that left the mirror itself, and look directly at the beginning of time? Astonishingly, the answer appears to be yes, and the message has been on its way to you for the entire age of the universe. There is a wall at the edge of astronomy, and every telescope ever built has stopped at it. When we look out into space, we look back in time, and the further we look, the younger the universe we see galaxies as they were billions of years ago, then the first stars, and behind them the oldest light in existence, the cosmic microwave background, released about 380,000 years after the bang. Behind that, nothing can be seen, not because nothing was there, but because the infant universe was opaque, a glowing fog of plasma, dense enough that light could not travel a finger's width without scattering. Every photon from the first 380,000 years was absorbed and reshuffled beyond recovery. Light, our great messenger, is silent about the very beginning by physical law. But light is not the only messenger. Gravitational waves, ripples in spacetime itself, the trembling of geometry that Einstein predicted and that instruments finally caught in 2015 do not scatter off plasma. To a gravitational wave, the fog at the beginning of time is no fog at all. The early universe is transparent, the way glass is transparent to sunlight. A gravitational wave born in the universe's first instant would sail through the plasma era untouched, ride the expansion of space for 14 billion years, and arrive tonight carrying information from precisely the place no photon can speak of, the bang itself. The beginning of the universe is not hidden. It is merely broadcasting on a channel we have barely begun to tune. And the mirror universe makes a sharp, characteristic prediction about that channel. At the seam, the mirror surface, where the temperature approached the Planck scale, the ultimate furnace of physics, 10 billion times the energy of a proton at rest, space-time itself would have been thermally excited. Gravitational waves in equilibrium with the primordial light, shaken to the same temperature as everything else. Those waves have been traveling and stretching ever since, and the arithmetic of expansion delivers a startlingly homely conclusion. Today, the relic gravitational hum of the bang should peak at wavelengths of roughly a millimeter, the width of a grain of rice. The first signal in existence, redshifted across the whole of time, now ringing at a scale you could hold between two fingers. Recall the contrast from earlier tonight. Inflation staked its reputation on colossal gravitational waves, light years long, imprinted on the microwave skywaves that decades of searching have not found. The absence that has been strangling inflationary models. The mirror predicts none of those. Its signature lives at the opposite end of the dial, short waves, millimeter waves, a thermal hiss from the seam itself, a channel no existing observatory was built to hear. Our kilometer-scale detectors, the ones that hear black holes collide, are tuned to wavelengths of thousands of kilometers. Millimeter waves would pass through their arms unnoticed, billions of times too fine. So, imagine the instrument that could hear them. It is not a fantasy. Physicists have begun designing and prototyping millimeter-band gravitational wave detectors, and the concept fits on a table. Picture it. A small crystal cavity, colder than deep space, suspended in perfect silence in a laboratory basement. Its atoms held so still that the apparatus can feel geometry itself twitch. You stand beside it, in the dark, watching a readout. And what the readout is measuring is the distance across the crystal, a distance that trembles by less than the width of an atomic nucleus, at millimeter rhythm, as a wave passes through you, and the crystal, and the earth, without pausing, now follow that wave backward. It has been in flight, unscattered and untouched, since before the fog cleared, before atoms, before light ran free, before the first second finished. It was emitted at the seam. If the mirror is right, the trembling in that crystal is the beginning of time, arriving live and continuously, 14 billion years late. Looking into that readout would be looking directly at the Big Bang, not at its afterglow, not at its consequences, at it. There is a catch, and Turok states it without flinching: sensitivity. To hear the relic hum, A millimeter detector would need to outperform today's instruments by a factor of roughly 1 billion. That is a mountain, but it is a mountain of engineering, not of principle. Prototypes exist and work. There is no roadblock, he says, only distance. And physics has climbed such mountains before. The detection of gravitational waves itself was dismissed as impossible for half a century until it happened, on schedule, to the millimeter of prediction. This field of speculating about the beginning of the universe, Turok says, has become the kind of field that can ultimately be decided one way or the other, decided by instruments. The oldest question there is, awaiting an apparatus the size of a desk. And so we arrive, at last, where the whole night has been pointed. Let us close the ledger together, in the quiet, and answer the question we carried in. 50 years of physics answered every mystery by adding new particles, new forces, new dimensions, new universes, and for 50 years, every addition failed to appear. Tonight we followed one stubborn idea in the opposite direction. Subtract until only the truth is left, then ask the truth to do all the work. The known laws, Einstein's gravity, the standard model carried through the one place everyone said they failed, turned out never to have failed at all. The singularity was a smudge on our map. The equations glide through the bang, and the unique continuation on the far side is a reflection, a mirror image of everything. Made lawful by the one symmetry nature has never once violated. Out of that single boundary condition, unpurchased and unadjusted, came the rest. A topological reason the bang had to happen, an arrow of time pointing downhill on both slopes of the seam, a vacuum balanced by 36 silent fields that forbid themselves to be particles. The triplicate parts list of matter, explained after 90 years, the fluctuations on the oldest light, amplitude and 4% tilt, traced to known constants of known physics, and the dark matter, named the quietest particle in the universe, filling the one empty chair the standard model always kept, 5 numbers on a table at the start of the evening. 2 now claimed outright derived, not fitted, for the first time in the history of cosmology. The other 3 accommodated with nothing invented, and the whole structure lashed to a mast. If the lightest neutrino weighs anything at all of this is wrong, and we will know within a few years. That is the simple theory that explains everything, not a theory of new things, a theory of no new things. The laws you already trusted, the particles already in the books, folded once, at a mirror, at the beginning of time. Is it true? Tonight was honest with you at every step, so it will be honest now. No one knows. The calculations are young, the assumptions are being tested, most of the field has not yet followed, and the history of cosmology is a graveyard of beautiful beginnings. Turok himself, who says plainly that most of what he worked on across his career turned out to be wrong, whose own teacher helped invent the very superstrings he walked away from, claims nothing more than a first hint. But a first hint with dates attached. Euclid is mapping the sky now. The double beta decay experiments are counting now. Somewhere in tonight's data, the lightest neutrino already weighs whatever it weighs. The universe has long since written its answer, and we are merely slow to read the envelope. Either way it opens, something rare will have happened. A theory of everything will have been judged, not admired, not elaborated, judged, the way Maxwell was judged, the way Einstein was judged, by the sky saying yes or no. And whichever way it goes, one image from tonight deserves to stay with you. Turok was asked, near the end of that long conversation, what drives him, a man in his late 60s, most of a lifetime spent on ideas he now calls wrong, still working at the edge of what he calls virgin territory. His answer had no equations in it. Life is a miracle, he said. To be alive is a miracle. We only live once, and so you had better make the most of it, and when you stumble across a chance to understand something no one has ever understood, you have to jump at it. Every night, people fall asleep beneath a sky they assume is mostly answered, and the truth is closer to the opposite. You are living inside an open question, in the brief, bright interval while it is being decided. And the deciding is being done by people who know their time is short and jump anyway. So consider, one last time, the mirror. All night, it has been a piece of mathematics, a boundary condition, a bookkeeping of the beginning. But it earned its name honestly. A mirror adds nothing to the room. It invents no second candle, conjures no stranger behind the glass. There is no one behind the mirror, there never was. It simply holds a boundary so perfectly that everything on this side becomes complete, self-contained, whole. That may be the final shape of the deepest truth we have, a universe that needs no additions, no hidden rooms, no one behind the glass, a universe that is, at its beginning as everywhere else, simply and entirely enough. The universe is enough. What we already know may be enough. And you, lying here at the end of this long descent and return 14 billion years downstream of the seam, made of third-generation stardust, warmed by a vacuum that balanced its books to 120 decimal places, you are one half of a reflection. Complete. Thank you for spending this night with me at the mirror at the beginning of time. If this slow walk through the simplest theory ever proposed brought you some wonder or some rest, a quiet like or subscribe would mean a great deal. It is how these long nights keep getting made. And remember, the next time you catch your reflection in a dark window, raising its far hand as you raise yours, the universe may have begun exactly like that, and needed nothing more. Good night, and may you never look at a mirror the same way again.